Okay, friends, we're going to look at this second option of projectile motion type problem. An object is being thrown off of a height at some angle. And this is where our trig is going to come in. You practiced this last week where we broke an angled vector down into its two components. So if I give you some velocity at an angle, we have to break it down into the x component and the y component. In this case, breaking down an initial velocity in the x direction and the y direction are going to give you two values to put on our table. We're going to get the initial velocity in the y direction, and we're going to get the velocity in the x direction. Remember, that's constant, so that value is always going to be whatever we find it is using trig. One thing to be really careful with is we have to consider a reference frame here, because this is like our problems where we were throwing them up and they were coming back down to earth. So we have to indicate is up positive or is up negative, and then we have to keep all of that matching while we're talking about our y, our constant acceleration values. All right, so let's try one out. This is the one we just did. Here we go. Quick reminder, if this is our angle here and we're given an initial velocity, we can break it down using sine and cosine to solve for initial velocity in the y direction and our velocity in the x direction. All right, a beach ball is thrown with a velocity of 5.7 meters per second at an angle of 20 degrees off of a 15-meter tall cliff. So I'm going to draw another picture just so I can kind of indicate. Let me make this bigger. I learned this trick just now. Come here. Woohoo! All right, here's my beach ball. It's being thrown at an angle of 20 degrees. It's kind of hard to see, but I think you can get it here. Let me clear that up. There we go. And it's being thrown at an angle or at a velocity of 5.7 meters per second. All right, so what we've ended up with is a vector that looks like this. Okay, we're going to use some trig. I'm going to draw in my x component and my y component, and then I'm going to use trig to solve for each of those values. So I know that my adjacent leg is going to be this one, and my opposite leg is going to be this one. So I'm going to use cosine for my x component, and I'm going to use sine. And cosine is adjacent over the hypotenuse. So, cosine of theta, fatal mistake there, is equal to whatever our Vx is, or our x component, all over the hypotenuse of 5.7. So if I do some math, I get 5.7 cosine of 20 is equal to the x velocity, right? And I can do that over here too. I'll do all my math in just a second. Sine of theta is opposite over the hypotenuse, so sine of 20 is equal to my initial y velocity over 5.7. Do some math, and my initial y velocity is 5.7 sine of 20. So if I plug those in, making sure my calculator is in degree mode, I get a value of 5.3 meters per second, maybe 5.4 if I'm rounding correctly, and 1.95. Okay, so this is great because now I have two values to put in my table. I'm going to separate it into x and y, and I'm going to list out the variables that I have to keep track of. A and t. I know right away we're talking about an acceleration due to gravity, and so I can plug that in 9.8 meters per second squared. At this point, I'm going to talk reference frame. Let's choose down and left as negative. And so my acceleration is going to be negative. From my calculations, I know Vx is 5.3. I know VOY is 1.95, and I'm launching this upwards at an angle, and so I know that this is going up, so it better be positive because my reference frame says down is negative. From there, we need at least one more thing on one of these sides, and it looks like we're falling from a cliff of 15 meters again, and that's going to be our delta y. Remember, we're going down, so it's going to be negative. Woohoo. Okay, at this point now we're ready for some math. We have three things here. we're trying to find how far it is from the base, which is our displacement in the x direction. I need an equation that can solve for time because I need a second value over here. From our three equations, I want to avoid the one that has t and t squared because my initial velocity is not 0. And so to get around that, I need to solve for a final velocity. And so I'm going to start here to a delta y. My final velocity in the y direction squared is equal to my initial velocity in the y direction squared plus 2 times my acceleration times delta y. So this is what I'm going to solve for. This is 1.95 squared plus 2 times a negative 9.8 times a negative 15. I'm running out of room over there. Apologies. So if I do this math, 1.95 squared is 5.75 plus 9.8 times 2 times 15. Those negative cancel. So I get 294. Add those together. Get Vy squared is 299.75. I'm going to take the square root of both of those, and I get 17.3. That's pretty fast, meters per second. And I need to consider, is that going up or down? At the end, right before it hits the ground, it's going downward, so that's going to be a negative 17.3. Great. Now I can use my other equation. Do you see how these patterns are very similar to what we were doing last week? I can use my other equation to solve for a time. And so I get a negative 17.3 is equal to a positive 1.95 plus a negative 9.8 t. Being really careful with my reference frame because it could really mess up my algebra. So 17.3, I'm going to subtract 1.95 from each side, and I get, so I'm going to go over here, 19.26. A negative 19.26 equals, you can't see that, here we are, negative 9.8 t. Divide each side by 9.8. Negatives cancel each other out, and I get 1.96 seconds. Whew, okay, but I'm still not done because I'm trying to find a displacement, but I'm getting closer because I know that if my time over here is 1.96, it better be over here because we're talking about one motion. We're just breaking it up into two directions. And so my last piece, I know velocity is a displacement over time. So my displacement is just equal to velocity times time. If I plug in what I know, 5.3 times 1.96, I can find out that I'm going to travel 10.4 meters from the base of the cliff. Woohoo! Go team!